And after this part, we'll go to the virtualization part. So today is the last part for the concurrency. It's about thread. Let's start from an example. Let's say we have a server, web server, and we have many clients. And if no parallel, which means the parallel processing capability in the server, then the server will have to process each client's request one by one. For example, client 1 first, then client 2, and then client 3. But if we have parallel, that means we can let the server process multiple requests simultaneously. For example, the several users they send the requests to the server, and the server will distribute the request to different workers and let them complete the workload processing and then reply the clients. This is a parallel processing. And for such a system, it has some requirements to build this program, the parallel processing program. For example, the parallel service on a multiple processor system, because we need multiple processor to process multiple tasks at the same time. So the web server to have multiple requests, and this system needs some requirements. First is the processes that can execute in parallel, which means multiple processors, and also it has its capability to process the tasks in parallel. And it also needs IPC. We discussed this in the first part of this concurrency. So, for example, we use the shared memory and the message passing to let the processes communicate with each other during the processing. And we also need a scheduler. That means we need to schedule different processes in parallel. And let's take a review on the process. We discussed this in the first part of the concurrency. A process, it has an address space for all the code and the pages. So the OS resources and accounting information, and also it has a PCB, process control block. And in the PCB, we have the information associated with each process, which means each process has its own PCB and also has a program counter and the status of the process. Of course, it has some registers and memory and the file descriptor. But creation of a process is expensive. So for example, if we want to create a process, all the process structures, we need to create new. And for example, the page tables, that we must allocate this resource to the new process. And we also have the context switching. It's also expensive. We discussed this before. Every time we do a context switch, that's a pure overload to the system. So the system is totally idle during the switch. And also that there's a problem is the IPC, the communication between different processes. It's very expensive, which means time consuming and resource consuming. So under this background, we need lighter approach to handle the multiple process. In general, a lightweight is good in computer systems. That means more parallel and higher resource utilization. And what are the similarity in these processes? During the, for example, in this is parallel server. So These processes are almost doing the identical task, which means here every client, they send their request to the server, and the server is processing almost the same identical tasks, and that means they share the same code and data, right? For example, a website, when the user click with different user, they click the same button. For example, in online shopping website Amazon, you click the order button, they're going to go to the same code part, and they share the same privilege. And also they shared almost everything in the process. But there are some elements they don't share. For example, its own program counter. Of course, each user, they have their own process, and different processes can be on different state because they are running on the different program counter, and also they have different registers and the stack pointer. So the idea is, why don't separate the idea of process from the minimal thread of control? For example, the PC registers. That means the basic idea about the thread. So each process has one or more thread within it, which means we need to create the thread or run multiple threads in one process. And for the process, the address space and the general process attributes, they share these things. And for the thread in the process, it's a sequential execution stream within a process. And each thread has its own stack, CPU register, etc. Again, these information are in the same process. Multiple threads information in the same process. And all threads in a process, they share the same address space, which means the memory space and OS resources. And thread now is a unit of the CPU scheduling. And the processes are containers in which the threads executes, and each thread is bound to a single process, which means it can only be working in one process. It cannot work for two processes. This chart shows the structure of the thread and the process. For example, this is a single thread process. In this process, there's only one thread running, and all the resources belong to this thread. But if we run a multi-threaded process, that means we can run multiple threads in one process. And each thread, it has its own resources, like registers and stack and PC and program counter. But they also share something like the code, the data, and the files. And this is called TCB. Just like the PCB, and for the thread, each thread, it has its own TCB. So this chart shows the memory layout of the process. We discussed this before many times. And for the stack, it contains some temporary data, and for the heap, it has a memory dynamically allocated. And the data is a global variables. Text is for the program code. So which sector need to change to support threads? Several parts. First one, the stack. Stack for the thread 1, the stack pointer for the thread 0, and for another thread 1, the stack pointer will be different. And if we have one more thread 2, That means we need one more thread pointer for this thread. So all threads in one single process share the same address space here. And for the program counter, we can store them in here. So that's how we allocate the memory to different threads in one process. So compare these two different methods. A thread has no data segment or heap. It belongs to the process. And a thread cannot live on its own. It must live within a process. And it's inexpensive to create, and also it doesn't need to switch everything like the process. So it's very it's lighter than the process switching. And if a thread dies, then the thread specific data and the resources are reclaimed, and the process is safe, which means the process is going to handle this part. And for the process, a process has code and data and heap and other segments. That's why every time we create the process, we need to allocate all of these resources to the process. And there must be at least one thread in a process. That's a requirement for a process. And it's expensive to create because we need to allocate memories and create the data structure for the process, and expensive for the context switching. And if a process dies, then its resources are reclaimed, and all the threads in this process will die. And we have two types of context switching in threads. And first one is between two threads in the same process. In that case, we don't need to change the address space because they share this part. For the TCP, it's much lighter than the PCB. And the second type is context switch between different processes. In that case, we must change the address space because that means the context switching happens on different processes. So that's the process switch. And there are many, almost all modern applications, they are multi-threaded. Like the website and social media, they need to process different tasks at the same time. So multiple tasks with the application can be implemented with multiple threads, and like the update display and fetch data in the background, or do the spell checking when you're typing, and the loading bar or progress bar. When working in the background, the progress bar is also working at the same time. And this thread creation is lightweight, especially compared to the process creation. And it can simplify the code, increase the efficiency. And the kernels are generally multi-threaded.